In the last few lectures, if you recall, we were discussing how to implement a particular processor. Now, as an example, we took the MIPS 32 reduced instruction set computer architecture, and we looked at how we can have a pipelined implementation of a subset of the MIPS 32 instruction set. Now, in this lecture, what we shall be looking at, that whatever we talked about with respect to pipelining of the MIPS 32, there you recall we had identified the 5 stages: instruction fetch, decode, execute, memory access and write back. And we also mentioned what are the required micro operations for the different stages. So, we shall now show how we can translate that description as we have presented in the last lecture into Verilog code directly. Okay. So, the topic of our lecture today is Verilog modeling of the processor, the first part of it. So, when we translate the micro operations that we have discussed in the last lecture into Verilog, there are a few things to remember. See, here we have identified 2 variables and they are used for very specific purpose. But before that, let me just tell you once more that how instructions get executed in a pipeline. Okay. Suppose I have instruction I executing. So, it will be going through fetch, decode, execute, memory access and write back, then instruction I plus 1 comes. So, it will be delayed by 1 cycle like this, then I plus 2 comes, it will again be delayed, and let us say I plus 3 comes. Fine. Now, let us suppose that we have a sequence of instructions that we have written, and the last instruction is a halt instruction. So, when we execute halt, the machine is supposed to stop. Let us suppose, let us just assume that instruction I plus 1, let us say, was the halt instruction. Let us assume this was the halt. So, there were some instructions before it, I minus 1, I minus 2, there were some instructions before it. You see, this halt instruction will be decoded during the ID phase. So, it is here after instruction fetch is done, we will be knowing that this is actually a halt instruction, but we cannot stop the processor right here. Why? Because the previous instruction which was here before halt, that has still not completed. It was still here in the EX stage only, and the instruction before that I minus 1, that was in the MEM stage, and the one before that was in the WB stage. So, you cannot stop the processor as soon as you detect it is halt, but rather you wait till the write back stage is reached and only then you halt the processor. But you remember that the halt instruction was found. So, you maintain a flip flop kind of a thing, this we refer to as halted, say a single bit variable. You set this flip flop to 1 whenever you find there is a halt instruction. So, what this will do, you see, just after the halt instruction again some more instructions will automatically be entering the pipe, but the machine is supposed to stop here, these should not be executed. So, while you execute an instruction, you check whether this flag is set or not. So, instructions I plus 2 and I plus 3 will be finding and will be detecting that this flag is indeed set to 1. So, it will not be doing any write, Like if it was a store instruction, it will not be writing into memory, and if it is a register instruction, it will not be writing into the register. So, writing will be disabled, okay, if this halted state is there. Now, similar will be the case if let us assume a scenario, there is a branch instruction, let us say branch equal to 0 something, and there are some instructions after that also. Let us assume again that this I plus 1, this was my branch instruction BQZ. So, it is during ID you detect that it is a branch, and if you look at the micro operations, you will be identifying only at the end of EX whether the branch is actually to be taken or not, because the target address is also computed and also the condition. Let us say I have specified here R5, it is jumping to some label loop. So, it will check whether R5 is 0 or not, that is also done in the EX stage. So, whatever instruction has been fetched in the next cycle, if the branch is actually taken, then this will have to be discarded, right. So, because of the same reason we maintain another flip flop, this we call as taken branch. So, it means whenever you detect in the EX stage that the branch is actually to be taken, that the condition is true, you will actually have to go to loop. So, you set this variable to 1 again, and all the following instructions which have already entered, it will be checking this variable. If this variable is equal to 1, it will similarly not write anything in the registers or memory. So, this is as good as saying that all the instructions which are following the branch, they will not be executed, right. So, this is one change that we are making with respect to the, you can say, the micro operation that we have seen means earlier during our last lecture. So, these are the 2 points I now just mentioned. So, we are using two 1-bit variables, halted and taken branch. The reason I have already explained, right. Fine. Now, let us straight away come to the Verilog code. This is the header of the description of the pipeline where we declare all the registers. So, you see here in this module the inputs are only the clock, nothing else, because instructions are coming from memory, they will be loaded in memory, that is all. There is no separate input that is coming to the processor, only clock 1 and clock 2, let us say, these are inputs. So, just like the last example of pipelining we discussed a few lectures back, we shall be using a 2-phase clock, and stage wise we are identifying all the variables that are required, they will be part of the interstage latch, and we are using the same variable naming convention that we have mentioned last lecture. PC program counter will be a 32-bit register, and in addition for the IFID latch you need IR and next PC NPC. For IDEX you need IR, NPC, A, B and IMM, these are all 32-bit quantities. Now, in addition we also maintain some variable called type. Well, type, let me just go ahead in the next slide and show you what is type. Type is actually the type of the instruction that is encoded in 3 bits. We are identifying a few classes of instructions like register ALU, we call it type 000, means type 0, register to memory ALU 001, load 010, store 011, branch 100 and halt 101. So, these are the codes that we are defining, and using parameters we can use these names instead of the numbers, right. Okay. So, after the instructions decoded in the ID stage, you recall during the ID stage instruction has already been fetched, it is stored in IFID IR, the instruction register, and from there the first 6 bits, you recall the instruction encoding, the first 6 bits are the opcodes. So, the opcode will be decoded and there you can find out whether it is an add instruction, add immediate, load, store, jump, whatever. Okay. So, depending on that you set this variable type, and as I said this type is a 3-bit variable. So, it is a 3-bit register and this type will be forwarded across stages. So, there will be one IDEX type that will be forwarded to EXMEM type, MEMWB type and so on, because in each stage you will be taking some decision depending on the type of the instruction. That is why we are keeping track of this information. Then in the EXMEM stage we have registers like IR, ALU out, B and a single bit variable condition cond. This is required for jump or branch condition checking. And MEMWB we have IR, ALU out and for load instruction load memory data LMD. Here we declare the registers. There are 32 registers 0 to 31, each of 32 bits. So, this is a register bank 32 by 32 and this is how we declare the memory. Memory we are assuming there is 1024 words, each word of 32. So, the memory is 1024 by 32. Well, here in this parameter declaration we are defining the opcodes which we have already discussed in an earlier lecture. We had assigned some 6-bit opcodes to all the instructions and this parameter is actually summarizing that. So, instead of referring the opcodes by their bit patterns, we will be using just add sub, then add immediate and so on, because it will make our Verilog code much easier to understand. Okay. We just using parameter, this example illustrates, we can make our code more readable because we can immediately know what that number actually stands for. Okay. So, here all these opcodes they are assigned a mnemonic ADD, SUB and so on. So, we have assigned opcodes to all the instructions we are considering, right. Okay. Now, this we have already showed, these are the types and these are the 2 single bit flip flops I mentioned. Halted, this will be set after the halt instruction is completed in the write back stage after the halt instruction reaches WB, and taken branch is another single bit register which will be set after you decide that you are taking a branch, and that is known only at the end of the EX stage, as I have mentioned. Only at the end of EX stage you will be able to set this variable, so that all the following instructions which have entered the pipe, they can check that value of the variable and they will know that, well, the branch instruction is actually been taken. So, we must not make any changes anywhere. So, all writes will be disabled. Okay. Fine. So, now let us look at the different stages of the pipeline. This is the instruction fetch stage. Well, in instruction fetch stage it is triggered by positive edge of clock 1. Well, we do this only if halted is not set. If a halt instruction has already set the halted flag, that means there is no need of fetching any further instruction. So, we execute this block only when halted, this flag is equal to 0, this flip flop. Now, what do we check here? First, in this if statement we are checking whether there is a branch which is being taken. How we are checking it? You see, we are first checking whether the opcode, you recall in the instruction register the opcodes were bit number 26 to 31. So, we are checking whether the opcode is equal to BEQZ. Well, in the parameter we have already defined the bit pattern for BEQZ. So, it is B branch equal to 0 and the condition flag equal to 1. So, what this condition flag will represent? This condition flag will actually represent this condition this register A, you recall the output of the first register that you are fetching, this equal to 0. This is the expression you are assigning to cond. Cond is a single bit variable. So, if this is true, cond will get 1, if this is false, cond will get 0. So, if the register value that is fetched in A is 0, then cond will be 1. So, this condition says that if it is a branch equal to 0 instruction and it is actually equal to 0, that means cond is 1. So, you have to branch, or it was a branch not equal to 0 instruction and cond was equal to 0, that means it was the register was not equal to 0, that means cond is 0. If either of these is true, which means we have to jump. In that case, what do we do? So, this instruction register we do not fetch from PC, but rather we fetch it from the address which is calculated in EXMEM. You see, for the branch instruction, as I said, at the end of the EX stage, the address of the branch is already calculated and stored in EXMEM ALU out. So, you take the address from there, that memory location you load in IR, and you set the taken branch flip flop to 1, this variable to 1, indicating that we are actually taking the branch, and this is the address from where you are fetching the instruction. So, now my PC or the NPC which is pointing to the next instruction must be this plus 1, just the next address, and else if it is not a branch is not taken, then it is the normal sequence of execution. You fetch the instruction from PC, then increase PC and NPC both by 1, right. This is the instruction fetch stage. Then let us come to instruction decode. So, in the instruction decode, you recall we basically do 3 things. First one, we actually decode the instruction, well, which we are not showing in the Verilog code because it is implied in the case statements. Secondly, we are prefetching 2 source registers, and thirdly, we are sign extending the 16-bit offset. Okay. Let us see how we are doing that. So, here again we start by checking the halted flag. If halted is 0, only then we do it. If halted is set, we skip. Well, here when you are fetching the registers, you make a special check. You recall I mentioned that R0 is a register, special register, which is assumed to always contain the value 0, nothing else can be written to R0. So, here we are checking, you see bit numbers 21 to 25 is in the instruction register, this represents the first register operand. Just you recall again, in the instruction register, the first 6 bits is the opcode. So, it is bit number 31 up to 26. Then you have register source 25, 21. Then you have RT, RT is 16 to 20. Then you have RD, RD is 11. Okay. So, here we are accessing RS, bit numbers 21 to 25. So, we check whether this is 0 or not. 0 means we are trying to access R0. So, if it is R0, then we do not access the register bank, you straight away assign 0 to this A variable. Otherwise, A is assigned to you access the register with this register number. So, whatever 5-bit register number is there, that is RS, that will be loaded into A, IDEXA. Then you load the second operand, which is in bit number 16 to 20, same thing. If it is 0, you load the value 0 to B, otherwise you read from the register, this is your RT field, load it into B. Then the other routine things, this NPC you simply forward it because we need it later, IF ID NPC will go to IDEX NPC. IR also you forward to the next latch stage, and immediate here you are doing the extension, sign extension. So in the IR, bit number 0 to 15 indicates the offset. So this will be the last 16 bits, and the highest 16 bits you take bit number 15, replicate it 16 times. I said the sign bit will be replicated, replicate it 16 times and then concatenate. This will become a 32 bit quantity. Okay. So immediate is created by sign extension. Then you also do another thing, you check the opcode again. This is the opcode, bit number 26 to 31. Depending on the opcode type, you set the value of this type. This type, you recall, we have already defined 3-bit codes to the different types, and using parameter, instead of writing 0000001, we can write it in a much more readable way like RRALU, RMALU, load, store, etc. And these are the instructions. These opcodes also have been declared using parameter. So you understand now what is the advantage of using parameters. Our code becomes much more readable. So now you can actually see by looking at the code that, well, yes, we are looking at the add instruction. Otherwise, seeing the opcode, you have to look at a table that, well, this opcode means add. You will have to refer every time. Okay. But this makes your code more readable, right? Fine. So if it is either add, subtract, and, or, set less than or multiply, you call it as the register to register ALU type. If it is add immediate, subtract immediate, SLT immediate, call it as RM type. If it is load word, load, store word, store, branch NEQZ or branch EQZ, it is branch, HLT is halt, and by default if it is something else by chance, then also you make it halt. There is an invalid opcode case. Okay, just one thing, this ID stage is triggered by clock 2. Okay. Then next comes the EX stage, which is again triggered by clock 1, and the way we start it is the same. We check the halted flag. So if it is equal to 0, only then we do it, otherwise we skip it. First we forward a few things. Well, this EX type, whatever type we have calculated earlier in the last stage, will be forwarded to the next stage. This IR is also forwarded, and taken branch, you see, taken branch, this variable was set in the IF stage, right? If you see earlier, so in the IF you had set this variable here. Because of this, the next instruction that we will see later, that will not be allowed to write into the WB stage, but all instruction after that again should be allowed to continue, because they will be starting to fetch from the correct address, because already program counter has been updated. So now we are resetting the taken branch back to 0 here, right. Now here, depending on the instruction type, we are carrying out the operations. There is a case on type, IDEX type. So if it is register ALU, then again we use a case statement on the opcode. This is opcode. So if it is add, subtract, and, or, SLT or mul, you specify what you are doing. If it is add, IDEX A and IDEX B are added, result is stored in ALU out. If it is subtract, subtract, and, or. If it is set if less than, you just do a comparison, less than. If it is true, then 1 will be stored in ALU out. If it is false, 0 will be stored in ALU out, and mul is multiplication. And if it is an invalid opcode, then you just load this undefined XXX in ALU out. Next, if it is registered to memory RM ALU, if this type, then again you look at the opcode. These are the 3 kinds of RM ALU instructions. Add immediate. Here you will be adding A with the immediate data. Subtract, you will be subtracting immediate data from A. SLTI, you will be comparing less than A and IMM. rest is same. Okay. Then if it is load or store, then you are calculating the address of the memory, address of the operand. What you do? You simply add the value of A and IMM. So, this will give you the address of the memory. This is stored in ALU out, and the value of B is forwarded because this will be requiring for stored instructions later. And if it is branch, then you see this is where you take the decision. Branch, you calculate the target address of the branch. How you do it? The value of the program counter NPC is added to the offset IMM. So, here you are calculating the target address if you have to take a branch, and also you are evaluating this variable cond, right. Now, you see this ALU out and cond which you are calculating in the EX stage. Let us again go back to the IF stage. You are actually using them in IF stage. You see, you are looking at this cond and this branch address. These are being used here. Okay. So, now you can understand from EX mem how they are coming. They are actually getting calculated here. Fine. Let us move on to the mem stage. This is again triggered by clock 2. So, again if this halted is 0, only then you execute this. So, what you do? Type is forwarded, IR is also forwarded, and here again there is a case statement. Well, let us make it uniform. Here I did not put this #2. I have given a delay just for notional purpose. Let us use the same delay everywhere, #2. Fine. So, if it is a register to register RR or RM, you do nothing, just you forward ALU out to the next latch. If it is load, the address of memory is already in ALU out, you have calculated in the last stage EX. You access memory and store it in LMD. And store, well, in store you check whether taken branch is 0 or 1. If it is 1, you do not do a write, disable write. If taken branch has been 0, only then you do the write, whatever is there in B, that you store in the memory location. And lastly, in the write back or WB stage, here triggered by positive edge of clock 1 again, here you check if taken branch is 0, only then you do it. If taken branch is 1 means someone is taking the branch, you disable the writes here, you should not write into the register. These registers, these instructions are actually dummy instructions, they should be ignored. So, what you do? If it is a RR ALU, you recall there the destination register is stored in bit numbers 11 to 15 in the instruction register. So, ALU out will be stored here, that is RD. If it is RM, it is stored in RT, bit number 16 to 20. And if it is load, again the data is in LMD, it will be stored in RT, again 16 to 20. And if it is a halt instruction, it is here in the WB stage, you are setting this flag halted to 1. So, that after you have halted, you have set the flag to 1, all further instructions will not do anything else, it will, the machine will basically stop. Okay. So, with this we come to the end of this lecture, where basically we have translated the micro operation that we discussed in our last lecture to Verilog. Of course, we have done a few things that are very specific to pipeline implementation, like those 2 additional flags we have maintained, and we have checked those flags at the beginning of every stage, whether that flag is active or deactive. If necessary, we skip some stage. Okay. So, in the next and final lecture, what we shall be discussing, we shall be looking at some example programs that you want to run on this processor we have designed, and let us see how it works. This we shall be seeing in our next lecture. Thank you.